So let us solve some more problems in thermodynamics. Now, in today's class, the problem one is this one. 1 mole of Fe2O3 and 2 mole aluminium are mixed at temperature 25 degrees centigrade, and the reaction completed to give. Now this is the reaction: Fe2O3 solid plus 2 aluminium solid, giving us Al2O3 solid plus 2 iron liquid, and enthalpy change for this reaction is negative 850 kilojoules. This is such an exothermic reaction that so much heat will be liberated, and because of that heat, iron will come out in the form of liquid. And this reaction has a great place in the history, which was used to connect the broken railway tracks. So the rails are connected using this reaction, which is known as a thermic reaction. Now this is the data, and the actual question is the liberated heat is retained within the products. Very big question. Within the products whose combined specific heat over a wide temperature range is about 0.8 joules over gram Kelvin. The melting point of iron is 1530 degrees centigrade. Show that the quantity of heat liberated is sufficient to raise the temperature of the product to the melting point of iron in order to get it welded. So this is the problem. So in this reaction, great amount of heat will be released, and that heat will make the iron into a liquid form. That liquid will be poured in the place where there is a requirement to connect the two iron pieces. So let's prove that there will be so much heat released that heat will be enough to melt the iron. Okay, what we need to know, we need to find out the heat. So first of all, the heat released in this reaction will be retained by the products, and we must know how much amount of products are there in the grams. Now, if we see the problem, the quantity of iron oxide, which is basically iron 3 oxide here, used is 1 mole, and how many moles? Actually 2 moles. 2 mole. So basically, if you see the mole ratio here, 1 is to 2. So that means here stoichiometric amounts of iron 3 oxide and aluminum are used. Therefore, both are limiting reagents. Therefore, we can find out that the products are also formed in the same mole ratio. The product Al2O3 will form in 1 mole amount, and iron element will form in 2 moles. Therefore, what are the mass of the products now? Now let's find out mass of the products. Mass of products equal to, first we get 1 mole Al2O3 plus 2 mole iron. So let's convert them into grams. So 1 mole Al2O3 mass is aluminum is 27 times 2 54 plus 3 oxygen 16 times 3 48, that is 102 plus another one is iron. So what is the iron molar mass? Iron molar mass is, so iron molar mass, that is 56 roughly. So there are 2 moles of iron, 2 times 52. So 2 times 52, sorry 56, 2 times 56, that is 112 grams. So therefore total is 214 grams of products are forming in these reactions, and these products are retaining the heat with them. So therefore how much heat will be released? Let's find out. What is the formula? Q equal to ms delta T. Okay, now here what is the mass? We have 214 grams times what is the specific heat? The specific heat given as 0.8 joules energy will be released when 1 gram of the substance temperature is raised by 1 Kelvin. So here 214 are there, therefore 0.8 joules over grams times Kelvin times what is the temperature change. Right now we have at 25 degrees centigrade, and what is the melting point of the iron? 1530. So let's add 273 to the temperature so that we get it into Kelvin. So 1530 plus 273, that is 1803 minus 298. So that will be equal to, this is Kelvin. So Kelvin, Kelvin cancels out, and grams, grams cancels out. So that will give us, if we do the mathematics, 214 times 0.8 times 1803 minus 298. Wait a minute. So I got 257,656 joules of heat will be released in this reaction. So that is equal to 257.7 kilojoules. So heat required here, how much given in the problem? Let's find out. The heat released here is, the heat required is 850 per 1 mole basically. So but here how much heat is released? 257. Yeah, 850 kilojoules. Okay, heat required is less than the heat released. So therefore the temperature can be easily raised by the required value. So here 257 kilojoules of heat is releasing, which is less than the temperature required. Therefore the iron will come into liquid form. So that's the first problem. Now let's go to the second problem. The second problem is this one. Calculate W and delta U for the conversion of 0.5 mole of water at 100 degrees centigrade to steam at 1 atmosphere pressure. Heat of vaporization of water at 100 degrees centigrade is 40,670 joules per mole. So what are we going to find out here? We are going to find out work change in internal energy when 0.5 moles of water at 100 degrees centigrade is going to steam. Okay, so here we need to find out how much volume is going to change. So therefore, so here 0.5 moles of water is going to liquid form. Therefore, what we write, n equal to 0.5. And what is the pressure? Pressure is 1 atmosphere. And what is the temperature? 100 degrees centigrade. That will be 373 Kelvin. So what we require is volume. So volume is coming from the formula PV equal nRT. That gives V equal to nRT over P. So what is n here? 0.5 times R is, so when we have pressure in atmospheres, we must use R value in liter atmospheres. 0.0821 times 373 divided by 1. So that gives volume equal to 15.3 liters. Okay, so this is the volume of the steam. But what is the volume change here? The volume change is actually the volume of the steam minus volume of the liquid. So basically liquid volume of 0.5 moles, basically 9 grams of the water. It's almost negligible. So therefore the volume change here basically volume of the steam. Therefore we can say that change in volume is equal to the volume of the gas, which is okay, let's say 15.3 liters minus volume of the water. So that is almost negligible. So that's going to be 15.3 liters. Now we have a volume change. What is the work done? Work done is equal to P external times delta V. Okay, so now here, now what is the sign of the work here? Here, work done by the system. So basically we must use negative side. So that's going to be negative P. What is the external pressure here? External pressure is 1 atmospheres times 15.3 liters. So we end up with negative 15.3 liter atmospheres. This is the amount of work done in liter atmospheres, and we must convert that into liter atmospheres. Why? Because he is asking the answer in liter joules. So therefore we must convert into joules. Therefore we know that 1 liter atmosphere is equal to 101.3 joules. So what we get here? We get the amount of work done is 15.3 times 101.3. So I got 1549.9 joules. So this is the work done by zero point 0.5 moles of H2O. But here we need to find out for so this is the work done for zero point 0.5 moles of the gas. Okay, but what is the heat required to convert the steam to water? This is 40,670 for 1 mole of substance. For half mole, that means zero point 0.5 moles, how much energy is required? That's going to be 0.5 mole times 40,000. 40,000, what's the number? 670 joules per mole. So this and this will cancel out and we get, so 40,000, 40,670 times 0.5. So we get 20,335 joules. So this is the heat required to raise the temperature, to raise the 0.5 moles of water at 100 degrees centigrade to steam. So this is heat. And remember here vaporizing, therefore heat must be a positive side. So therefore, according to first law of thermodynamics, what is the relationship between internal energy change, work and heat is delta E is equal to Q plus W. We just found that heat is 20,335 joules and what is the work done? Negative 1549.9. Therefore that's going to be negative 1549.9. So we will end up with, this is 20,000, this is 1500. So we may get around 18,000. 20,335 minus 20,335 minus 1549.9. So that's going to be 18,785.1 joules of gain of internal energy. Why it is so? The total heat the gas, that is water, is absorbing is not using it to provide some work. So most of the heat out of 20,335 joules is retained and very little work done, which is 1549.9 joules of the work done. Remaining 18,785 joules of the work is retained by the water. Now, third problem. So that is calculate work done when 50 grams of iron is dissolved in HCl at 25 degrees centigrade in a closed vessel and 2 in an open vessel or beaker, whatever it is, when the atmospheric pressure is 1 atmosphere. So this is the problem. Okay, so when we carry out the reaction in a closed vessel, there will be no loss of gases. But when we carry the reaction in an open vessel, if any of the gaseous products are released, they will escape into the outside surroundings. So therefore, there is a slight difference between the closed system and open system. The open system, the matter will escape into the surroundings if the system is consisting of gases. That is the problem. So let's see, when there is a reaction carried out in a closed vessel, is there any value change? There will be no value change because it's a closed vessel. So in closed vessel, a residue vessel, you could say closed vessel, delta V is equal to 0. Then why? There is no change in value. So therefore, what is the work done? Work done equal to negative P external times delta V, which is simply 0. Only in the open vessel work is done because the gas released will expanding into the will going into the surroundings. That's why there will be some work done. So let's find out what is the reaction between iron and HCl. So that is iron plus HCl is giving iron Cl2 plus H2 gas. This reaction is not balanced. Therefore, let's try to balance this one. If I make 2 moles of HCl, the reaction is balanced. But look at here, the problem is actually 50 grams, but here 1 mole of iron. So here 1 mole iron producing 1 mole H2 gas. So 1 mole of iron means 56 grams iron producing 1 mole of H2 gas. So that means how many grams of hydrogen gas we are getting. Okay. So when 56, when this is 56 grams is 1 mole. But in the problem we have 50 grams. Therefore, what are the moles of iron? Moles of iron is equal to mass over molar mass. That is 50 grams divided by 56 grams per mole. So that's going to be 50 divided by 56 moles. And look at the relationship between iron and hydrogen. That is 1 moles. Therefore, we can say that moles of hydrogen also, moles of hydrogen gas is also 50 divided by 56 moles. So now we got the moles. Now let's find out the delta V. What is the delta V here? Volume of the gas minus volume of the liquids, which is basically negligible. So therefore here, let's find out the value here. To find out the value, what is the equation? Ideal gas equation, PV equal to nRT. So from that I can say V equal to nRT divided by P. So we have N value 50 divided by 56 and R value we know that is 0.0821, and temperature, what is the temperature we are doing? The reaction is carried out at 25 degrees centigrade. That is going to be 298. Okay, so if we do the mathematics, let's do it. 50 times 0.0821 times 298 divided by 56. So I got 21.84 liters. So this is the work. So value change happened. So that is therefore what is the work done? So work done is equal to negative P external times delta V. That's going to be negative 1 atmosphere times what is the delta V? It is 21.84 liters, because the liquid reactants is almost negligible value. Therefore, the value change is 21.84 liters. So that gives negative 21.84 liter atmospheres work of work is done. So what is that in the joules? The work done is equal to negative 21.84 liter atmospheres times 1 liter atmosphere in the denominator. This is 101.3 joules. So that's going to be this liter atmosphere will cancel out. I got 2212.84 joules of the work done by the system. So this is the answer. This is the expansion work done by the hydrogen gas released when 50 grams of iron reacts with hydrochloric acid in the open vessel. In the closed vessel, there is no work done because there is no expansion of the expansion is taking place. So that's the answer. So this is for the class today, and the next class also we will be doing some problems. Thank you very much.